How's it going, everybody? Today I'm coming to you to pose a question. And the question I have is, could you use a needle like this one that you would get on a dress shirt or something like that, a straight pin really? Could you use a needle like this to perform materials characterization? And that's going to be the topic for today's lecture. Here's an experiment you can do at your house. I'm here in my garage. I have different materials. I have a piece of wood, which is the top of my workbench, a piece of ceramic tile, a 3D printed chicken, a lid, plastic lid, and a piece of paper. And so you can do this also at home. It's kind of in the same vein as the first kind of at-home activity we did during the beginning of the semester in the first introductory lecture. And I want you just to take your fingertips. So fingers, it's a sense of touch. Your fingers have a lot of sensitive nerve endings in them. Mine have pretty much lost most of their feeling because I keep cutting my hands doing various crafts and stuff like that. But I want you to take your fingertip and just rub it on any surface really, but try to do more than one so you can make a comparison. So I can touch the wood. It's actually pretty nicely sanded and smooth. I can touch the ceramic tile. It actually has a rough texture to it. I can compare plastic to plastic and see that my 3D printed chicken is a little bit rougher than this nice injection molded lid. And then even a piece of paper. And it's a little, I don't know, kind of soft. So kind of think about that. We can get an idea of smoothness by taking our finger and just dragging it on the surface, okay? Now what I want you to do is kind of repeat that, okay? Repeat this, but use your fingernail instead. And we kind of start getting kind of other feedback. Just kind of think about it, even close your eyes if it helps. So you kind of rub your fingernail on it, and you actually kind of start getting almost like a vibration interaction. So I can really tell now that this is rough and that this is smooth and that the wood is also pretty smooth, but it's almost softer because it starts actually resisting the dragging of my nail, my fingernail. So my fingernail now becomes a probe. Should have gotten a manicure. And then this, and I also almost can kind of tell that this is a harder surface now. So I'm not poking it, you know, like pushing the Charmin at the grocery store if you're lucky enough to come across Charmin. But I can actually almost tell that this is a harder surface. So give it a try. I encourage you to do that. And this paper now feels very soft when I drag it, okay? So now we're using the back of our finger. I don't think there's as many nerve endings under the fingernail as there is on the tip. I'm not quite sure, but I venture to guess there's not. Now we can take our straight pin. We can take our straight pin now and drag it on the same surfaces. So we can drag it on the wood and kind of hold it very lightly between the tips of your finger and thumb, which is probably the best way to do it. And we get even more kind of a feedback response. And if it helps to close your eyes and do it, it's pretty cool. You could probably even use a pencil or something with a sharper end. It's a little more precise than the back of your fingertip. And I even start getting sound, right? Almost like a record. If you drag it on this, you kind of see that the softer materials almost resist the dragging of the needle. And so some things that you want to kind of take away. One, your finger tip is pretty blunt, so you're not going to get as much resolution. Your fingernail is smaller, but we're actually getting some vibratory response, right? Because your nail is attached to your finger. So you get some vibratory response, which is kind of nice. So you can kind of tell the difference. And I will assert that you get a better resolution when you're using this needle. Okay, so there's some analogies now that we will explore in the area of probe microscopy. But I encourage you to try this stuff. If you don't have a straight pin, I mean, just telling the difference between the tip of your finger and rubbing your nail over it, it's pretty profound if you think about it. And so let's move on now and start talking a little bit more about surface probe characterization. We're talking about surface characterization still, so I've titled this lecture Surface Characterization 2. Last time we talked a little bit about what this micrograph is. It's a Mr. Clean Magic Eraser. And we did, or hopefully you guys gave it a go using your finger, or if you found a straight pen, using a needle, I guess, to do some characterization of materials. And there's an instrument that works pretty much the same way as dragging your finger across the surface, and that's called a Stylus Profilometer. And so this is a type of surface characterization, Stylus Profilometry, if you will. And it basically drags a stylus across the surface, and you get information. So you can get information such as film thickness, and I've personally used one of these instruments before. If I want to read along with my poorly punctuated slide here, the surface is physically touched by a stylus probe, although I think there's newer models now that work on electrostatic forces, basically. So there's actually a flavor of profilometry that's contactless. But the classical Stylus Profilometer is a touching mechanism or touching type of characterization. So you have to be careful. It can be considered a destructive test. And so in the earlier part of my time in the semiconductor industry, Stylus Profilometry was what was used. And you make silicon wafers in a whole bunch of them called a lot. And you would take one of these wafers, and it would kind of be the sacrificial lamb, so to speak, and you would measure the film thickness. So process characterization in that manner is not used these days. It's not good enough for today's modern design rules, which are on the, I think, single-digit nanometers. I was looking up the spec for the latest Snapdragon, and I want to say it's about 7 nanometers. Anyway, I digress a tad. I'm probably dating this lecture with putting design rule specifications. But for surface and stylus profilometry, the surface is physically touched by the stylus probe. The movement of the stylus in Z is converted to an electronic signal, and there's some sort of movement, so combined with X and Y movement, I'm giving you topological data. A lot of times the movement in X and Y is on the micron scale, and that can be achieved with stepper motors, actually. But the vertical resolution's in the nanometer range. And again, the drawback is you have to touch the surface, and so you could actually destroy what you're looking at if you have a very sensitive material. Of course, putting a needle on a surface and getting an electronic signal is nothing new. We have record players, which have been around for some time. And I'll go ahead and pause it so it's DJ Jazzy Jeff. Actually, tribute to vinyl. In my day, DJing was all done on vinyl. Now it's electronic. But anyway, a record player is a good example of running a needle over a surface and getting a different type of signal. We hear sound, but there's some conversion going on in here, which is converting the basically roughness within the groove of the record to an electronic signal, then to sound. Of course, the old like gramophones basically took the vibration of the needle and converted that into sound, and also recorded sound on wax. And I have kind of this interest in that. I probably should have put some slides together on that, but I think that would be way of a digression. But a stylus profilometer actually works very much like a record player. And here, I guess more specifically, these are turntables, but a record player. So a stylus profilometer, this is an older one. This is a KLA 10-core alpha step IQ. And if you look, it actually kind of looks like a record player. It's circular because it was actually designed for the semiconductor industry. And again, chips are made on wafers. If you want some more information on that, I'm happy to tell you, or you can just Google it. This is a KLA 10-core alpha step IQ. It's an older version. They have newer stylus profilometers because they still find a place in particularly research labs. And again, a stylus is dragging on the surface. The stylus is very, very small, and the smaller the radius, you get better resolution. And if you did the experiment with a needle, you can hopefully visualize that you're getting better resolution with your finger than the needle. And for this particular type of product, the tip radius actually has a pretty good range, and they can be pretty small. 100 nanometers to 50 microns is the range that KLA Tencor advertises on their website. And so a stylus, it's a very, very sharp object, drags the surface, and you insert it by hand into kind of the gantry there. The question you want to ask is, how is movement translated into an electronic signal? Well, you have this needle riding, okay, so you have a whole gantry where this needle is riding, and that's done with a linear variable differential transducer. Sometimes it's called a transformer. I'm missing the end of my parentheses there, I'm sorry. But the movement, so the stylus moves, which then moves the magnet, and I kind of have a weird, kind of horizontal to, vertical to horizontal kind of translation in my depiction. It doesn't have to be this way. It can be vertical to vertical. But your movement moves a magnet through these induction coils, basically, and that converts it to an electronic signal. This is a very high-level explanation. But a linear variable differential transducer, again, sometimes called a transformer. This is very interesting, very important. You can get similar information as to that of a cross-section. And so I did a lot of work with Conductive Ink in the past, and I was actually manually, I was forced to manually measure my trace by the SEM because I had done all of my calculations based on profilometry, because it's much faster to get data off a profilometer than it is to get data off of a SEM cross-section, because you have to prepare the specimen. And this was an article. I didn't cite it very well here. I'll probably try to edit that in later. But there is an article that I was struggling to get published actually as a PhD student because the reviewer didn't believe my profilometry data. And so I made this SEM cross-section and proved that, the maximum height of roughly 10 microns that I got off the profilometer correlated well with what you would measure off of an SEM. And so you can get similar information to a SEM cross-section with a profilometer. So in my mind, it's still a pretty good instrument. Scanning probe microscopy is kind of the next topic we're going to jump to. So we're kind of doing things a little bit fast. And you also have some accompanying reading in the book. But scanning probe microscopy relies on attractive and repulsive forces to generate information about a surface. If you can see me, we have my two hands coming together representing atoms. And atoms have a positive nucleus, basically, and then negative electrons surrounding them. And I go into great detail in this in electronic materials. I know it's also an intro to metallurgy, so this should be classic to you guys and gals. But you have temporary attractive and temporary repulsive forces due to the movement of the electrons and whatever the net positive and negative forces. Anyway, we're relying on these attractive and repulsive electrostatic forces, we want to just call them for lack of a better term, to give us information about the surface. In most cases, this is a little bit different than Stylus Profilometry because the probe does not actually touch the surface in most cases. There are flavors of atomic force microscopy where you actually are touching the surface. And this evolved from emission microscopy technology. And we talked about that on day one, and we'll kind of revisit that slide in a bit. I like always talking about the history of where these instruments came from in some degree or another. So in 1936, field emission was, I guess, discovered. And if you remember field emission, I talk about field emission in a greater detail when we talk about scanning electron microscopes, because that's a flavor of an electron microscope is a field emission electron microscope, and we have one in our metallurgy department. Field emission is basically when you apply an electric field to a tip and electrons are emitted from that tip due to the application of this electric field. That's also called cold cathode technology. And so just a few years before field emission, you could basically have thermionic emission was developed in I believe the 20s. And the thermionic emission is basically where you heat up a metal in a vacuum and it starts to emit electrons. Okay, so field emission is different than thermionic in that there's no heat involved, just an electric field. And so that's kind of a high-level summary. We'll talk about the difference between field emission and thermionic emission and Schottky emission when we start talking about scanning electron microscopes. But anyway, it's on this slide. Figured I'd talk about it just a little bit. So 1936, field emission was developed. 1956, the field ion microscope was developed. 1967, atom probe microscopy was developed, and that's C. So let me kind of go through with my laser pointer. So field emission led to the field ion microscope. Basically, we have a small tip, and so you can kind of see the size of the tip. So this is a very small tip, so roughly 1 nanometer for the tip radius, leading to the emission of electrons upon the application of an electric field, which is what this voltage is telling us. This led to the field ion microscope, and this led later on to the atom probe microscope, which led to the time of flight mass spectrometer, which is kind of an interesting instrument. We won't talk about it too much. Maybe we will pick it up later, but we'll talk about it just a tad. That led to the scanning tunneling microscope, and then finally the atomic force microscope. So kind of a lull here, I guess, between the 60s and 80s, maybe, for scanning tunneling microscope, atomic force microscope. Kind of want to break these up into 2 categories. Oops, wrong way. So on these 3, so field emission, field ion microscope, and the atom probe microscope, the tip is the sample, and that's static probing. And I was always taught that the tips were made by dipping the metal in acid and then letting the acid drip off like a icicle. And so you get these really, really sharp tips. And you could actually characterize then your specimen. Okay, so if you remember the field ion microscope, you zapped it with an electric field. It started to emit electrons, and you actually got lattice information. Scanning tunneling microscopy, and atomic force microscopy, the tip is the probe, and so this is so-called dynamic probing. So we have 2 flavors of probe microscopy now. So we have static probing, where your tip is the sample, and that only gets you so far, really, and it limits what you can actually look at, because you're limited by the ability to make your sample into a very, very sharp tip, basically, a needle, if you will, to kind of bring back in my original analogy that we talked about at the beginning of the lecture. In scanning tunneling microscopy, the tip is the probe, and also in atomic force microscopy, the tip is also the probe. And I talk about scanning tunneling microscopy quite a bit in electronic materials. Kind of a recap, on day 1, we talked about the field ion microscope. So the tip was your specimen, basically, and you applied an electric field. Electrons were emitted. Those electrons hit a fluorescent screen. You can then somehow take a picture of that fluorescent screen with a camera set up. And here we got lattice information. In this case, it was tungsten. This time of flight mass spectrometer, you put your needle specimen in, and you get a lot of information about it. So you can get chemical species information and that kind of thing. And the book talks about this in a little bit greater detail than I'm going to talk about, because I'm going to focus mostly on scanning tunneling microscopy and atomic force microscopy in the subsequent slides. Kind of going back to my question here, and I killed my, I didn't, it's static, excuse me, I couldn't read my own writing, so to speak. What enabled the transition from static to dynamic probing? We'll answer the question now. Piezoelectric devices, And so on a scanning tunneling microscope, there's typically 3 piezoelectric devices in the X, Y, and Z. On the AFM, the cantilever drives the piezoelectric with X and Y actuation, and Z is measured by a laser, basically. And piezoelectric, we'll kind of just give a really quick overview. And so if you change it, so delta L, so change in length over the original length, is equal to dE. So D is the piezoelectric coefficient, and E is electricity, basically. And it could also be voltage. So PZT, or lead zirconium titanate, is the most common material. Barium titanate is another, although lead zirconium titanate is a much better piezoelectric material. One thing is the Achilles heel of these systems is degradation, and so hysteresis oftentimes occurs with piezoelectric devices. And so I don't, off the top of my head, remember the lifespan, but they go through some hysteresis. Borrowed this from the book I was using for electronic materials. And so if you apply a force, you get a voltage. If you apply a voltage, you can change the morphology of the piezoelectric device. And so you can actuate by applying voltage to your device, or you can measure voltage by applying a pressure to the device. Again, kind of maybe a refresher to everybody. This is a centrosymmetric structure, so this is not a good piezoelectric. The piezoelectrics work because you basically create a dipole when you strain the lattice. So something that's like salt would not have piezoelectric properties because it's centrosymmetric. A non-centrosymmetric lattice, and so we're implying that piezoelectrics are ionic compounds, basically. But a non-centrosymmetric material, here we can apply pressure along the y-axis, and then we'll get a voltage. We'll make a dipole. If we apply pressure on the x-axis, we're not going to get voltage because we're not making a dipole, basically. And so non-centrosymmetric is what we call this crystal structure, and that's what you have to have if you want a piezoelectric device. So just a quick refresher there on piezoelectric devices. Scanning probe microscopy. The probe doesn't touch the surface at all in scanning tunneling microscopy, and the key there is the needle's riding on the surface, and it's typically metallic. So scanning tunneling microscopes, I believe, are limited to only conductive, I shouldn't say metallic, but conductive materials, because you have to get a tunneling current, and that's what's measured. So there's a better schematic in the book that I should have borrowed a little bit, but your movement due to attractive and, well, actually here, I shouldn't say movement every time, okay, because a scanning tunneling microscope doesn't always have to move to get a signal. The change in tunneling current actually gives you the signal in STM, but this is high level. So the measurement of attractive repulsive forces is then converted into an electric signal, and you can actually get imaging off of an AFM and an STM. And the big thing here is that you get sub-nanoscale resolution. And so it rivals and sometimes surpasses transmission electron microscopy in the ability to measure atoms. And so it's actually a very, very powerful tool. This kind of a refresher, and you kind of see these F versus R curves, so interatomic separation, or E versus R curves, which is again interatomic separation. So the force is kind of translated to energy between these two graphs, and this should be something you guys have seen since Intro to Metallurgy, so I won't talk about it too much. But the potential energy of attractive and repulsive forces are what's defining the response of this probe tip. Here we kind of have different regions. So we have 3 regions based on this potential energy curve that you then develop. If you remember, this is the equilibrium point if we have 2 atoms coming together. But we don't necessarily need to live in equilibrium point when we're talking about probe microscopy. But we have contact regions and non-contact regions and kind of the so-called intermittent contact region. And that has to do with the different modes, particularly in AFM, that we run by. And I think I have a supplementary video about scanning tunneling microscopy that I'm going to also have you guys watch. The probe tip radius, so very similar to Stylus Profilometry. The probe tip radius is what's defining instrument resolution. And even if the tip is much bigger than the feature size, you can still resolve the interatomic spacing, which is kind of an interesting aspect about this type of work. Scanning tunneling microscopy. So the electrons overcome the air gap barrier between the sample and the probe. And I'll throw another video for you guys to watch. I think it's actually really well done. What you get here, so your electrons, and I should show my better cartoon, but the electrons that are emitted, and typically the tip, the radius of the tip is a single atom in most cases for an STM. And electrons are emitted from that atom and they interact with the atoms of your specimen, and you actually get a current, okay? And so that's called the tunneling current. And the current and voltage is measured as a function of separation between the sample and the surface, basically. So you get some tunneling action. Kind of going back to tunneling, we kind of have the so-called lucky electron model. And so you actually got over the energy barrier, okay? We'll kind of just leave it at that. The Z is the width of your energy barrier, basically. So I kind of put the Z in. And again, you can get angstrom level resolution there. And if we want to talk about this a little bit more, let me know. I talk about it fairly extensively in electronic materials. And some of you hopefully have had this in other classes as well. But tunneling, basically, the electron gets over an energy barrier, hooray. There's other kind of models we can talk about in terms of like the lucky electron model. And I may throw that in this presentation, excuse me. Kind of some schematics talking about the different microscopes. So this is an STM microscope, and these are atomic forces. So the difference between an STM microscope, you're dealing with the tunneling current. The probe is riding just above the surface. On an AFM, the tip is actually on a cantilever. Okay, so it is a little bit different because you can actually move the cantilever. And so there's some other things you can do. So you can do contact and also contactless type of probing. And so here, the probe goes over the surface and it starts moving. You're measuring the Z with this laser, basically. Here, you can vibrate the cantilever and kind of get different information. And we'll talk about this in a little bit more detail on the different slides or subsequent slides. Operation modes for scanning tunneling microscope. So constant current mode, and the current is held constant, and data recorded as a change in height. And so here, the data is driven by the piezoelectric device, basically, that we talked about before. Constant height mode, the height is held constant and the current is difference, okay? Or the current changes and the measurement and the change in tunneling current changes. And you can kind of get an idea. So if I kind of try to create a topography with my finger and I have this probe, the tunneling current's going to be lower here at this cusp and it's going to be higher at the top. Okay, so you can convert that change in tunneling current directly to an image. And you can guess that the lower current would be darker and the higher current would be brighter, basically. So constant height mode. Here's some images from a scanning tunneling microscope, and I'll let you read. You can read it in the book or you can read it off of the slide here. But it's pretty awesome if you think about it, because you're getting really nice atomic scale images. And so very, very powerful tool. Atomic force microscopy. So I kind of jumbled through what I was saying on the schematic, but the probe is mounted on a cantilever. It's similar to profilometry, in terms of a touching stylus or a probe, like your record player even. It doesn't touch the surface in every mode of use, and a displacement of the probe tip is measured just like profilometry. So there's some differences here. You measure displacement in the probe tip only in one mode on STM. Constant height mode, you're measuring difference in current, and in this case, tunneling current. Okay, so AFM slightly different, but the biggest difference is we're on a cantilever. Here's an example of an AFM tip. So I actually got this out of the book, and it's pretty small. And the tip is actually on the nanometer range. And I have one in my office, but I don't have one with me here at my home. But anyway, here's what an AFM tip looks like. And it's made by similar technologies that are used to make microelectronics. So deposition, lithography, that kind of thing. Operation mode. So this is kind of the big deal for AFM. So contact mode, the cantilever is pushed against the surface with a constant force, giving constant deflection. And the deflection to the cantilever is sensed and the height is adjusted to compensate. And so that change in height is what you measure. Non-contact mode, so the probe's really close to the surface, okay? This is not tunneling because you're not applying a current to the tip, okay? So that's a big difference between AFM and scanning tunneling microscope, is you're not applying a probe current in an AFM. So here, the probe is staying 100 angstroms roughly above the surface, and it's responding to van der Waals forces. So it's going to move, and that movement is detected by the laser system. Tapping mode prevents probe sticking, and so it's actually oscillating. So you're oscillating this probe, so it's a harmonic oscillator. Oscillation, and so by itself, and I won't get too much into these, but anyway, by itself, the cantilever is a harmonic oscillator, so it's going. Attractive repulsive forces are acting upon the tip when it's near the surface, and there's a gradient to this force, and it's causing the frequency shift. And the measurement and shift is how data is collected, basically. And I may go into more detail on this. I may not, just because we have kind of a lot of topics. But the cantilever is a harmonic oscillator. So again, it's differing from STM, where STM, the probe, you're measuring purely a difference in current. Here, when you're oscillating your cantilever anyway, it's a shift in frequency of the oscillation is how the data is going. So I probably should have put here in tapping mode, you're actually measuring a frequency shift difference to figure out how high everything is. Measurement of movement, and I didn't cite the source I got from this, but it's later on. I'll credit this from the book. This is the schematic that's given in the book. So your cantilever is moving. You're hitting the cantilever with a laser. The laser bounces off and then goes through this mirror system, and you have these multiple photodetectors. And so the book depicts two quadrants. This article that I'll talk about in a little bit shows 4 quadrants. And I should probably fix that, but anyway. So the measurement of movement is laser driven. Here's kind of another schematic talking about the movement of the schematic of the AFM. So it's kind of a complicated instrument is kind of the point I'm making, but you can kind of read the accompanying text to this in your book. One thing that's very, very interesting to me is that AFM tips are used for different applications, actually. So you have this really small tip that's on a cantilever. If you oscillate it, you can control things. You can actually heat it up biasing, by heating up, almost like a light bulb. And so one method I came across a long time ago, actually, I thought was really interesting, was using an AFM tip for direct write applications. So you can essentially dip it in conductive ink and write very, very small electronic traces. When I lived in the Bay Area, I would ride my bike past this IBM research center. And in that research center, they were developing what was called millipede technology and millipede memory. And millipede memory is actually kind of neat. So this is the article. I got the picture for the other. In fact, let me just fix it, because I feel bad I did not reference this. And you're watching my, there we go. So it's fixed. Oops. Taking a long time. Okay. Sorry about that pause. Crediting other people's work is a big deal. I try to credit stuff. You don't want to be accused of plagiarism ever. And I don't want someone to think I drew this. I don't want to be a thief. So I'm using this for educational purposes, so I can borrow it according to copyright laws as long as I pay them homage. Okay, so made a mistake. Forgot to put that there. So you always want to credit where stuff comes from. So I got this depiction of the AFM from this article, basically. So moving on, IBM millipede memory, really neat. So you can actually heat up the AFM probe tip. I believe this material is actually cacalginide, which is the same material used in DVD RWs. And basically, you heat up the tip, you put in this little divot, and then kind of move right along. Then you come back and basically run it like an AFM to read the change in topography. And where you have the hole in your material, you got a 1. Where you don't have the hole, you got a 0. And so this was millipede memory. And this was memory technologies are important. And if you don't believe me, just think about every time your phone runs out of memory, unless you're uploading everything to the cloud. And cloud-based storage has kind of come in because cloud-based storage is actually advanced quicker than static memory. Anyway, so people are always looking for ways to replace flash memory. So here's 2 other applications for AFM tips. Here are some images from our textbook of AFM, and I don't think this is giving AFM the credit it's due, because I've seen nicer AFM images, and I challenge you to go maybe look some up. But this is out of the book. This is back in chapter 1, kind of showing AFM, and you kind of get this nice profile of something on a substrate. And this is kind of cool. It's graphite image to the limit of the AFM. And so this is 10 angstroms, so this is 1 nanometer, and so it's pretty fascinating. Actually, it's pretty cool. This is an atom. So AFM's very powerful tools, and again, it all developed from probes, so the ability to make very thin tips. If we look at the difference between AFM, STM, and profilometry, I always kind of like these tables. And so AFM, the probe touches depending on the mode. STM, the probe never touches the surface because you're dealing with a tunneling, so you have to have a gap between your probe and your surface. And profilometry, at least for the classical definition, the probe touches the surface. For AFM, attractive and repulsive forces are measured. And so the electrostatic forces are measured, and in tunneling, STM, the tunneling current is measured, and in profilometry, vertical movement is measured. And it's pretty, there's some similarities again between profilometry and AFM, at least for contact mode AFM. The AFM and STM, very powerful. They're on the angstrom scale, so we saw images of atoms. And profilometry, it's nanoscale, but typically only in the vertical. And I was going to have like a resolution comparator, and I still think STM has the best, but I've seen some really nice AFMs. And hopefully this has kind of answered how a needle can be used to perform materials characterization. I'll throw in a supplemental video about scanning tunneling microscopy, and I might throw something in about atomic force microscopy. But you're always free to go look up some stuff on your own, and I challenge you to do that and satisfy your own curiosity. So hopefully this has been informative, and thank you very much for your time.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.